All right, good morning, guys. This is April the 9th, and this is Rational Exponents. All right, so we talked about before how if you are multiplying or dividing or adding or subtracting radicals that do not have the same index, then you can't do anything with them. They have to have the same index to be able to combine them at all. So today we're going to show you how they actually can be combined by rewriting them and changing the index. Sounds crazy, really not bad, super easy. Okay, so the first thing you need to know is exponential form right here. Exponential form obviously has a exponent in it, right? So we have radical form, which has a radical in it, and exponential form, which has an exponent. So for exponential form, this is the nth root of a. In other words, an easier way to put this is the denominator of your exponent is going to be your index every single time. Okay, the denominator of your exponent is going to be the index. Then you put the radical sign. The base of the exponential form is going to be your radicand. And then that leaves the numerator, which is the power of the radicand on the inside. Okay, so going back to make sure you understand, rational means fraction. Anytime you see that something is rational, it means it can be expressed as a fraction, right? So we're going to have rational exponents, which are fractions in the exponent. So you'll see fractions in the exponent for all of these. So the same thing for the next one. We would have our index of n, because that's the denominator. We would put our radical sign. A is the base, so A is now the new radicand. And then m, whatever that number may be, will be your exponent here. Okay? So we're going to go straight into the expression, or straight into the problems. Hopefully it'll be a little easier for you to see. So for number one, writing it in radical form. In other words, we are going to have a radical in our final answer. Our index is a 4. That's our denominator. Then we write the radical sign. Our base is x, and that is being raised to the first power. So there's nothing else we can do there. We don't even need to write that 1, right? We're done. Just the fourth root of x. Okay, so for this one, for number 2, our index is a 2, so we don't have to write it. It's understood that there's a 2 there. Our base is 15n, so that's our radicand. And again, that's being raised to the first power. Really not bad. But it does say simplify if needed. So sometimes, like in number 3, where we have a cube root of 24 to the first power, we do need to simplify. So 24 there would be 8 and 3, 4 and 2, 2 and 2. There's our group of 3. It takes 3 to pop one out here because we have an index of 3. So we have 2 cube roots of 3. That other 3 is left over. So we do need to simplify sometimes. Let's skip down to number 5. We have a square root. K is our radicand, and then it's being raised to the 7th power. So here we do need to simplify as well, because the exponent on the inside is bigger than our index, right? So we're going to break that up into a multiple of 2, which will be 6. And then we'll simplify. So 6, k to the 6, divided by that 2 for the index, will be k to the 3rd on the outside. And we still have this other k on the inside. And that will be completely simplified. Now, you can also do this with numbers. For instance, number 6, if we have a fourth root of 3 to the 5th power, right? Fourth root of 3 to the 5th power. Now, you could take that 3 to the 5th power and multiply it out 3 and multiply it out 5 times. So that will give you a number, and then you'd have to split them back apart. Or you can look at it like this. If that's 3 to the 5th power, that's the same as 3 to the 4th power and 3 to the 1st power. So treat that 3 almost like a variable, like we did for number 5 with k, right? All you'll have to do is split that up so that you still have a multiple of 4 up top. Now, again, you can do it like I said and multiply 3 to the 5th power, and you'd get 5 3s. But either way, our index says that we have a 4, and it takes 4 to pop one out. So we're going to pop out 1, 3 because we have a group of 4, and then 1, 3 is going to be left over. So that's the exact same thing that we have here. I think writing it like an exponent and treating it like, writing it like a variable and treating it like a variable might help you out a good bit. So we'll do number 7, and then we will move on. We have a fourth root. Our index is a 4. And then AB in parentheses is being raised to the third power. Now there's 2 ways you need to do this. And one way is wrong. Well, there's 2 ways to do this, and one of them is wrong. If you notice that A and B is in parentheses, and they're both being raised to the 3/4 power, that means on the inside, A and B here also need to be in parentheses, because it's not just B that's being raised to the third power, it's A as well. And we know we are completely simplified here because the 3 is smaller than the 4. If it takes 4 of them to pop one out, there's no way we can do that if we only have 3 of them. If you'd like to write it like this, that would probably be the most simplified, I'd say. So that was going from exponential to radical. Now we can go from radical to exponential. We do the exact same thing. We're going to have our index is a 3. So I'm going to put the denominator right there with a 3. I'll put 16 as my base, and then it's 16 is being raised to the first power. That's it. So just the cube, or the cube root of 16 is 16 to the 1/3 power. For xy, we have a index of 2. We have xy as our base, and that's being raised to the first power. Now, you need to look at this one and say, how I've written it right here, that's only the y is being raised to the 1/2 power. Both of these are inside the radicals, so we need parentheses here. You need to be very careful with that. Make sure that both of them are being applied to it, okay? So for number 14, immediately what you see with 14 is like, there's a 5 on the inside. That can be simplified out. Yes, but they're not asking us to simplify. They're just asking us to write it in exponential form. So our index is a 4. Our base is a k. And it's being raised to the 5th power. That's it, right? That's all you have to do. So you'll kind of start seeing a pattern. Anything that is raised, anything that's a square root will be to the 1/2 power, as long as this exponent on the inside is 1. Anything to a cube root will be to the 1/3. Anything to the 4th root will be a 1/4. And you can keep going with whatever root they give you. I don't think I'm ever going to give you one that's higher than 4, but you never know. All right, so another thing for number 15, if you look at 15, I could go in and explain the reasoning for this, and I probably will real quick. This square root of 3m to the 7th power would be like writing the square root of 3m 7 times, right? And anytime we multiply radicals, we know that we can multiply them on the inside like that. So what I want you to understand with this is the way they've set up 15 is the exact same as if you had 3m on the inside and there was a 7 underneath the radical, and that 3m was in parentheses, because we would write this out 7 times underneath the radical. That's just one of the properties of radicals that we talked about with multiplying. So it's the exact same thing. That 7 on the outside is the exact same thing as putting a 7 on the inside, as long as that 3m is in parentheses. So here, 3m is our base, and it is going to be in parentheses. Our index is a 2, and we are raising that to the 7th power. So be careful with that. For 17 and 18, I'll just do 17, but I do want to show you kind of how this works. Anytime you have something where it has multiple different exponents in the denominator, here's what I want you to do. I told you up here that the square root of anything is just a 1/2, right? I want you to just put 1/2, because that's a square root, and leave everything else the same. That's it. And if you need to multiply out, if you're somehow combining later on and need to multiply out, you can multiply that 1/2 to the 5, 3, and 1. But you don't have to. To get it in exponential form, that's what we just did, and that is perfectly simplified. You don't have to go any further than that. So the whole point of exponential form and radical form, the great reason that we do this is so that we can combine terms and combine radicals that have different indexes. So here we're just using our exponent rules, and this will be adding, right? We're going to add the 1/3 and the 4/3, and that will be x to the 5/3. And now they're asking us to write our answer as a radical in simplest radical form. So we will have a cube root of x to the 5th. We will break that apart into x to the 3rd and x squared. And our final answer will be x cube roots of x squared. Again, you know you're finished because our exponent on the inside is smaller than our index. We need 3 to pop one out. We only have 2. Okay, so the whole point in this is exemplified really well in number 20. If I had go ahead and change this into radical form, if I was given this in radical form, which I'm not, but let's say they actually gave you a step above this that was the 4th root of p times the square root of p cubed, right? Which is, I just changed these back into radical form. So if you look up top here, if this was our first step that they gave us, obviously we can't multiply these because your indexes are not the same. But if we change them to exponential form, like this, now we can combine them together because we will add these, right? We add those exponents. So that's 1/4, and 3/2 is the same as 6/4. So that will be 7/4. And now we can change that to radical form. Again, we just simplify. So that will be the 4th root of p to the 4th and p to the 3rd, p 4th roots of p to the 3rd. Okay, so even though beforehand we have different indexes, we now know how to change them to exponential form from radical form, and then combine them and then put them back into radical form. So if they had given us radical form to start out with, the way to combine these is to put them in exponential, combine them, and then change them back to radical and simplify them as much as possible. So we can do the same thing with all sorts of different ones. This 5/2 and 7/4 here, we're going to make that 10/4 so that they can be simplified. Our exponent rules show that we can, or say that we can subtract those exponents, and that will be the 4th root of m to the 3rd. That's it. For number 22, we multiply exponents when we use the power rule. So that will be a to the 5/6. We multiply fractions straight across. So we will have the 6th root of a to the 5th. There is actually a 6th root in there. All right, so continuing to